And welcome to another topic in chemistry. I welcome you to our lecture today. Our topic for today is going to be the chemistry of light. This is the first day of our Unit 7. If you are watching this video as part of Miss K's trimester Chemistry B, the date is March 19th if you're watching this on the day it was assigned. Otherwise, write down whatever date it is that you're taking these notes. And I welcome you if you're watching this at any other time other than March 19th. Our focus for today in the form of an essential question is, how is light produced? Go ahead and set up your focus note page, your topic, your essential questions you have in mind, what you should be able to answer by the time we're done. And then we'll take time for CASTA questions, and then you'll do a summary at the end, just to help you process these notes in addition to just getting new information. All right, let's get into it. All right, so light is the focus of our introduction to this unit. Light can be thought of in two different ways. So dual properties of light are, you can think of it as a particle, and you can think of it as a wave. Wave is what I want to focus on during this lecture. So how can it be a wave? How can it be that wave pattern that we think of in science? Well, remember that in matter is all made of atoms, and inside every atom there are electrons. And the charge on an electron is, think about what is it? It's negative, right? And the nucleus charge of that atom is, can you think of it? It is positive. Since you have a negative electron and you've got a positive nucleus, those opposite charges, of course, attract. And when you have that opposite charge of negative and positive, it creates something called force lines. And this is a visual representation of what force lines would look like. In fact, if you had a magnet and you sprinkled little pieces of magnet shavings around that magnet, you can actually see these circular patterned lines. So these force lines happen anytime you've got negative and positive charges or opposite charges attracting. Okay, so that has been established. So imagine that this is the nucleus, this is the electron, you've got these force lines between the positive and the negative. Okay, well, where does the wave come from? Well, electrons start at their ground state. We refer to that as N, so their energy level N. It's wherever they started in the electron cloud. So think of this could be energy level N for this electron. This would be energy level N for this electron, okay? Electrons don't stay still, right? So they're moving around in three-dimensional patterns, kind of more like, an ellipses, not a perfect circle like this. And if they gain energy, they don't stay near the nucleus. They can actually move to different energy levels. That is known as an excited state. So if this electron gains energy from a chemical reaction or from soaking up UV energy, like from the sun, this electron can actually move up one level, at least one level, in its ground state. But then it's like, oh, wait, this isn't my normal location. I'm going to lose energy and I'm going to go back down at least one level. But that goes over and over, over and over. Over and over, up and down, up and down. That's happening constantly in anything that is giving off light. Well, remember, there was those lines connecting the electron negative and the positive nucleus. Remember those lines that were there? So imagine it this way. If this electron starts moving up and down, these lines, these patterns will also move up and down, up and down. Do you start to see what I'm doing with my mouse here? Maybe you can start to imagine a wave pattern that looks like this. So if this was the negative, right? And the nucleus was here, this used to be a force line, just like a smooth curve like that. But when the electrons started moving up and down, the moving force lines create a wave pattern. But you know that there's lots of different wave patterns. This one's really, really, really smashed together. This one's more spread out, doesn't seem to move maybe as fast. So then how do we get different patterns? They don't all look the same. Well, the electrons could move up and down more or less energy levels, right? So if I only move this, like a little bit up and down, I get this kind of a wave. But if I move up a lot of energy levels and fall back a far way, up and down, then that wave would start to look different. So again, if I have an energy level here and I fall from here down to here, then that's going to move a wavelength that looks like this. But if I have a farther distance to fall, then I have a different amount of energy that is moving. So that would give me a different wave pattern. But the electrons can also move slower or faster. And you can have more or less electrons moving. So you could have one electron, like in hydrogen, that moves from here to here, here to here, here to here. If it has a lot of energy, maybe it can go faster, and that could give me different wave patterns. Or I could have a whole bunch of electrons, like this is potassium. It's got 19 electrons that can be moving up and down, and all of them can be moving different levels. Like all of these could be moving up to here. These all could be moving up to here and down here. So lots of different patterns can happen. So the point is, we get different patterns of waves depending on what those moving force lines look like as the electrons move. So the general idea, electron starts at its original location, it gains energy and moves up, it falls back down because it can't always maintain that energy. The up and down motion causes the force lines to move, and that creates these wave patterns. All right, think about that so far. Go ahead and do a level 1 question. These are your first notes for this trimester, so if you need the Costa question guide, it is posted on Schoology in the guides and resource handout folder. Find that. It's got sentence starters. Level 1 questions, remember, are more like definitions or list or something really straightforward right from the notes. Take a little break. Think about the notes we just wrote right now. Pause and write a Costa level 1 question. Come on back when you're ready. All right, so then the other thing I want you to think about is just what are the terms we use when we describe a wave? So if this is kind of a general picture of a scientific wave, let's review what a wavelength is. As it shows here, a wavelength is from one part on a wave to when the wave starts repeating. So not from top to bottom, right? That's not the length of this wave. It's when the wave starts to repeat. So here it's going down, and then here it's going up, and then here it's going back down, right? So from here to here would be a wavelength, or from here to here is a wavelength. So it is the length of a wave like it sounds. So it would be units of like centimeters or nanometers or meters, depending on what kinds of waves you are talking about. But that is when the wave starts to repeat, that is the wavelength. Frequency, kind of like the word sounds, it's like how frequently it happens. So if this is a wave and this is another wave, right? How fast did it take to get from this part to this part? Or if I've got a whole bunch of waves, like 10 different waves, how many seconds does it take for those 10 waves to pass by? So frequency is kind of like, think of it sort of like speed. It's not specifically that. A lot of times it's measured in something like waves per second, or hertz, that's known as. Maybe you've heard of that in frequency measurements, like radio measurements. So frequency is kind of like the speed of the wave. Wavelength is how long it is. And then amplitude is how far up it is from sort of the baseline. And then crest and trough. Crest is the high point. Trough is the low point, kind of like, animals eat out of a trough to help you remember the difference. So those are just other vocab words we use when talking about the scientific waves. Wavelength and frequency we will use a lot, so I want to make sure that those are terms that are familiar with you. Amplitude is a lot more useful. We use that in sound waves, right? Like an amp. You think about like how loud or soft it is. That has to do with amplitude, but we don't talk about it quite as much with light energy. All right. Okay, the other thing I want you to, another vocab word related to light is electromagnetic radiation. So we oftentimes, of course, think of light as what we can see, but I need you to realize that light in science is really all the different patterns, not just the visible ones we can see. So radio waves are a type of light in science. Gamma rays are a type of light in science because they're all electromagnetic radiation. These words are synonyms. And so you can see, okay, so if we think of wavelength patterns, these electrons are moving up and down a certain amount. These electrons are moving up and down a certain amount, and we get different patterns. And you can see that this is really stretched out. These are really, really smashed together. Has something to do with their wavelength, their energy, their frequency, and we'll talk about that next. But you might recognize some of these terms, but like infrared and radio and visible, this is known as the electromagnetic spectrum. Let's talk about that a little bit. So radio waves are generally okay for our body. So let's first of all just talk about waves and energy. So energy is the ability to cause change. So if you have waves that are high energy, they can cause a lot of change. Well, radio waves are pretty low energy, so it's okay for our bodies. It doesn't cause a lot of change like against our cells, which is good because think about how many radio stations there are just near Roseville. There's lots of radio stations, which means there's lots of radio waves all over the place. But when it hits our bodies don't notice that change. So radio waves, That means lowish kind of energy. Then you've got microwaves and infrared visible. So now this is a high enough energy that our eyes can actually detect it. And maybe you've seen this before, Roy G. Biv. It's the order of the visible light energy, red being the lowest, violet being the highest, because the next one is ultraviolet. So even higher than violet. And you know that ultraviolet light, not so good. What am I talking about? Yeah, sunburn, right? So depending on the pigment of your skin, some people are more susceptible to sunburn than others. This is just an extreme example. Plus, it's funny because it's, fancy sandals. But the point is that ultraviolet light is high enough energy that it can change our skin cells, and actually it can damage them in what we think of as sunburn. And then X-rays. So X-rays are a little bit higher energy. You don't want to have X-rays on your body all the time. This is why, like if you've ever been to the dentist, they put that lead apron on your body when they take the X-rays of your teeth, because they're like, hey, if you don't need X-rays anywhere else on your body, let's try to protect it a little bit. And then we got gamma rays, even higher energy. Oh, poor Bruce Banner. So those of you that are fans of the comic book, or if you've ever heard of the Incredible Hulk, the idea is that Bruce Banner was susceptible, or he had gamma rays that were put on him in, an experiment gone wrong, and then it changed his cells, changed his body into the Hulk, right? So, there is true science behind that. And then, of course, cosmic rays would be our highest energy that we've kind of been able to measure, and that would definitely be bad for our bodies. But cosmic rays, generally that's out in space, and we're not out in space unprotected, so it's not like we need to worry about that. But the point is that we've got different versions of waves, all based on the movement of the electrons. Okay, so now let's make some connection between wavelength and frequency. So radio waves would be a low frequency, so they're not moving very fast, and a high wavelength, meaning it would be really stretched out, right? So a high wavelength would be a long wavelength. It's really stretched out, lower types of energy. And then it just goes up from there. Microwaves would be a little bit higher frequency, a shorter wavelength, up until we get to like cosmic rays, which would be a high frequency and a low or a short wavelength, which might look like this if you compare the two. So short wavelength, meaning it has a lot more energy, it can move a lot faster, higher frequency. That would be the idea behind the connection of electromagnetic radiation and kind of frequency and wavelength, some of those other vocab words that we're talking about. All right, go ahead and pause the video and do a level 2 kind of question, a compare and contrast. You could do a sketch, sketch a microwave compared to an ultraviolet light wave. Like that would be a great example of showing a compare and contrast and also being able to draw. So do a level 2 question, pause the video, think about those notes so far, come back when you are ready. All right, so the next little section of our notes, I'm going to do some video demos to go along with some light examples that are pretty fun. All right, so go ahead and watch this first light video. So what you saw was fluorescence or fluorescing, right? So fluorescence, what happens was, what you saw was the electrons in the chalk were absorbing the UV light from that black light, and when the electrons go back to their ground state, they give off energy in the visible region. So they seem brighter than normal. So this is like black light stuff. So if you've ever done like black light bowling, or if you have black light paint in your, like on a poster in your bedroom, or there's fluorescent materials in laundry detergent. So clothes look brighter when they're out in the sun or in really bright lights. So they seem brighter than normal because there's extra energy in the visible region as the electrons fall back to their ground state. So the black light idea, just when the black light is there, the electrons absorb that. So that was the chalk. So the electrons in the chalk are absorbing the UV, and so you see it seeming brighter than normal in the visible region. But as soon as you put the UV light away, the black light moved away, you didn't see it because there was no extra energy to make the electrons move to their upper excited state, so they had nowhere to go back down to. So they were already at their ground state. So that was fluorescence, so black light stuff. All right, watch this next one. saw this time was phosphorescing. So it's glow-in-the-dark stuff, like glow-in-the-dark stars, or if you have a remote with like little glow-in-the-dark buttons on it so you can see it in the dark. So what I used in the video was actually natural phosphors. So like truly these were like glow-in-the-dark minerals that had been mined from rock somewhere. We've had them for, probably like 50 years sitting in a box in my old classroom, brought to my new classroom from 2 other teachers before me that used to use them. So I have no idea what the chemicals actually are. I just know they're natural phosphors. And you could see that the green one lasted a lot longer than the others, which is why the green version is what we see more than any of the other glow-in-the-dark colors. But the point that makes them different is they still absorbed energy from another light source, right? Like the sun or the light in your room, or in the demo, it was the UV light again. But then when the UV light or the light source goes away, the electrons go back down to their ground state slowly, which is therefore why you get that glowing sensation. So different than fluorescence, right? Fluorescence, as soon as the light source was gone, there was no more glowing of the chalk, right? Or the black light stuff. For phosphorescence, glows after the light source is taken away because the electrons go back down to their ground state slowly. So they're still gaining energy and moving up, but when they come back down, they go slower. So you'll stop glowing when all the electrons are back down to their ground state. Phosphorescence or phosphorescing. All right, watch this third one. So what you saw was chemical luminescence. It's what happens in glow sticks, right? Because you know the first thing you got to do for a glow stick is you have to like bend it or crack the inner tube of it so the chemicals can mix. And in the video you could see I tried to show it with like the big funnel in the tube. It was just too light in the background. So that's why I just put it in the Erlenmeyer flask in the front so you could see that glowing. So the 2 chemicals mixed together, and what happened was it was an exothermic reaction. So that chemical reaction from the 2 chemicals mixed together gave off energy that's exothermic. So then the electrons can absorb that energy that was given off, gets them to an excited state, and then they release energy again in the visible region, that glowing. And then they go back to the ground state. So think about it. When do you think it stops glowing? Yeah, when the reaction is done. So when the chemical reaction is done, then you don't see any more glowing. So some chemicals take longer to get back to their ground state. Some chemicals give off different colors. It depends on it. So this chemical reaction is different from this chemical reaction because you've got different colors. And if you think of like the visible spectrum, Roy G. Biv, so this blue is giving off a higher energy than the orange. Those electrons must be falling farther, meaning they are giving off more energy as they go back to their ground state. And then when all the electrons go back to their ground state, then that reaction will be done. You won't see any more light. So to the idea that people say, oh, put your glow sticks in the freezer, it'll last longer. Well, think about what you know about energy. So if the electrons are moving up and down and coming back down is what makes them give off light, well, if they're colder, they will move slower, which means, yes, they will take longer to go back down to their ground state. So there is truth to that. However, it's in your freezer, so you can't see it. Because as soon as you take it out of your freezer, they're going to warm up and they're going to go back down to their ground state really fast. But the point is, there is some truth to that idea. All right, related to chemical luminescence, the last thing I want to mention is something called bioluminescence. So if you think about the English language, bio has to do with life and luminescence is still light, right? So basically this is chemical luminescence in a living object. So it's what happens inside fireflies. They've got a chemical. What happens is if they get startled or they're trying to mate or they're trying to warn other bugs, what happens is they literally like fart chemical into their little tail, and that mixes with the other chemicals that are already in the tail, and that produces the light. Or maybe you've seen some of those deep sea like fishes, or there's in Finding Nemo, there's this little animal that it's so dark down in the way, way, way deeps of the sea and the ocean that you can't see the animal at all. It just has this bioluminescent like lure on it, and then some other fish are attracted to that lure, and then it can chomp and it can eat that thing. So bioluminescent is just this cool thing of chemical luminescence, but happening, the living object is producing the chemicals that create the chemical reaction for the light. All right, so go ahead and do a level 3 kind of question, some type of predict or imagine kind of thing, or judge. Those are always kinds of fun kinds of things. But if you need an example, there's that Costa guide on Schoology to help you with some sentence starters. But pause the video, think about our notes so far, write a level 3 kind of question. All right, and then for your summary today, what I'd really like you to do, because if you think about our EQ was, what is the chemistry of light? So for today's summary, write an explanation of how light is produced and see if you can do it in 3 steps. What happens first, then what happens for light to be produced? That's what I want you to try to be able to say in our summary. And that brings us to the end of this video lecture. Here's your to-do list. If you didn't already, this is a reminder if you're watching these notes as part of my Try 3 class, go back and finish any of the intro stuff from the first day of class and any of the review assignments that kind of reviewed stuff from Chem A. So that was specific to this class. If you were just watching this video for any other reason, you could finish your COSTA questions that went with these notes for today and also write your summary. The purpose, again, of these COSTA questions and summary is that it helps you process what you just saw. So it isn't just random information that you wrote down or listened to, but did you understand it and make it part of your actual learning? All right. Thank you so much for your attention and for learning more about light and chemistry. I look forward to seeing you next time. Bye.